Okay, so now continuing with chapter 2, we are going to look at radioisotopes and how they decay. We'll look at two processes here and one in the next section. So we've looked at isotopes, and we understand that isotopes are kind of different versions of the same atom, and those different versions have different number of neutrons in the nucleus. And since neutrons are neutral charge, they don't have a charge, they don't really affect much in terms of chemistry or the properties of the element. But we do need to recognize that some isotopes are radioactive, and a lot of isotopes are actually radioactive. While there's a few there may be a handful of stable isotopes for an element, many are radioactive. And radioactive simply means that the nucleus isn't stable. So after a certain amount of time, and we'll talk about that in a little bit, the nucleus falls apart to try to make a more stable nucleus. And a lot of times that will make different atoms. But a lot of times it also involves the emission of smaller particles, alpha particles or beta particles, or just energy. And we'll talk about all that here in a second. Before we go too far, though, I want to show you kind of where you can find information about the different isotopes. Individual isotopes are also called nuclides. They're called nuclides because when we're dealing with radioactivity, we're dealing with the nucleus. And different nuclei are called nuclides. So I'm going to show you this table of nuclides here. Oops, probably need to get off my pen and just go back to something else. And if I click on the table, this link that we've done there, I get a table of nuclides. I'm going to drag that over into our window here. And what we have here is this table of nuclides is from actually South Korea, I believe. It's the best one I think there is. And what we see is this interesting graph on the right that's very colorful, or on the left that's very colorful, and it's got two axes. And the top axis and the left axis, the vertical axis, is the atomic number. And you can see it's Z, that's just the letter we use to describe atomic number. So that's the atomic number. Remember, atomic number determines what element you have. And along the vertical axis, the x-axis, is the number of neutrons in the atom, N. Okay, so this is all the elements. I'm going to zoom in a little bit so we can see what this looks like zoomed in. I'm going to click the plus sign a couple times. I'm going to do it one more. There we go. It's a little slow today, and that's okay. What we should see is those colors, but we're zoomed in, and we should see the be able to see the individual elements. Come on. There we go. There we go. So we've zoomed in enough. Remember, the Y, or the vertical axis, was the number of protons, the atomic number. So we can see this at the low end here where Z is 1. These are hydrogen isotopes. Remember, H1, or hydrogen 1, is the name plus the mass number. And in hydrogen, or hydrogen 1, the mass number, remember, is the number of protons plus neutrons. So hydrogen has 1 proton, and hydrogen 1 has a proton and no neutrons. And that's actually the most common version of hydrogen. There's also hydrogen 2, which would mean the mass number is 2, so 1 proton, 1 neutron, and so on. Okay, the colors here are very important. So the black elements, the ones in black, those are the stable isotopes. Those are the ones that don't radioactively decay. The nucleus is stable. All the other ones are radioactive. Okay, so you can see most most isotopes that we know about are radioactive, and only 1 to maybe 7 or 8 per atom are not radioactive. And as we get to bigger ones, there could be more that are stable. So what you can see is, what I wanted to show you here is that there's a lot of isotopes or nuclides for each element. And for each element, there's a couple that are stable, maybe 1 in the case of fluorine, while all the other ones are not stable. So I can scroll this a little bit and go to our bigger atoms. And we can see, some of these, like calcium, has 1, 2, 3, 4, 5, 6 stable isotopes, and many not stable. All right. The color actually has to do with the half-life, and we'll get to those here in a little bit. All right. So I wanted to show you that. The link is in the PowerPoint, but I will also, at the end of this chapter, I'm going to discuss a couple different online resources that are really cool, and this is one of them. Okay, going back to our slide here. So if we have an unstable isotope, a radioactive isotope, a radioactive nucleus, it will, after some time, break apart. And it will break apart and it will emit things. In this case, it's emitting, or it could emit an alpha particle, it could emit a beta particle, and or it can just emit high energy light, which we also know as electromagnetic radiation. Okay, and those are called gamma rays. So, there are over 300 naturally occurring isotopes, and 36 of those isotopes are radioactive. So most of the ones we saw on the table of nuclides are man-made. Okay, but we will look at kind of naturally occurring isotopes. So all the isotopes of elements having an atomic number greater than 82 are radioactive. So if we look at lead, anything bigger than lead is basically radioactive. There aren't any stable isotopes after lead. There are over 2,000 man-made isotopes, and most of those are all those are radioactive, and those are called artificial isotopes. All right, so in everyday living, as we go about our days, we're going to always get, what do I want to say? As we walk around, we're going to get radiation hitting us. There's nothing we can do about it. There's naturally occurring radioactive isotopes that exist not only in our bodies, but just in the earth. So this radioactive decay is going to produce alpha and beta particles and gamma rays, and our body is going to feel some of that just because it's a natural process. Okay, the sun produces is a big nuclear reaction, and it produces a lot of particles that hit the earth, and we live on the earth, so we get hit by some of those. Clearly, and that's called background radiation, the radiation that we have no control over, that just is naturally occurring. What we try to do then is minimize the rest of the radiation that we are subjected to, and we'll talk about that a little bit here coming up. Okay, during radioactive decay, an unstable nucleus, an unstable isotope, breaks apart into typically a small atom, and releases a particle or energy or both. Okay, and when it does so, the product is called a daughter nuclide. So the initial nucleus, or the initial isotope, is called the parent. That's radioactive, and after it breaks apart, it makes a daughter nuclide and maybe an alpha particle or a beta particle or gamma radiation, gamma rays. Okay, so the product, the daughter, could still be radioactive and go through its own radioactive decay, or it may be stable and that decay will be done. So let's look at the two different types of particles that are produced through radioactive decay. The first we're going to talk about are alpha particles, and it's called alpha decay when the parent nuclide decays and produces an alpha particle. And an alpha particle consists of 2 protons and 2 neutrons. Okay, and since these are high energy things, there's no electrons around it. So when a nucleus releases a particle that has 2 protons and 2 neutrons, that is an alpha particle. Okay, usually large nuclei that contain lots of protons and neutrons and are radioactive will emit alpha particles to try to get to a nucleus that's a little bit smaller and more stable. All right, so the symbol for an alpha particle is alpha with a 4 and a 2. And remember, those numbers are what we talked about when we were doing symbols for isotopes. The top is the mass number, so that's the number of protons and neutrons, and we can see that's 4 because there's 2 protons and 2 neutrons in an alpha particle. And the lower number is 2, that's the atomic number, and that is the number of protons, and there's 2. Okay, sometimes it's written like this because it's got no electrons, so there's just 2 protons and no electrons to make it neutral, so it's actually got a 2+ charge. We'll talk about that in another chapter, but you can see that is shown here also. Okay, so basically what this is a helium atom that has no electrons. Remember, helium has atomic number of 2. It's got 2 protons in it. Most helium atoms have also 2 neutrons. So this is basically a helium atom that has lost its electron. So it would be called a helium ion. Okay, so if we're going to write a reaction for this, or an equation that depicts this reaction, it would look something like this. So, for example, in this case, we're showing the parent nuclei as radon-222. Radon is actually a noble gas, but it's not a stable noble gas. It's reactive. It's one of those things that we test for in basements of houses now to ensure that you don't have radon in your basement. If you do, it's a pretty simple solution. We just put a little pump, a little fan, and blows out. It just circulates the air in the basement so that radon doesn't build up. Okay, so we have radon-222, which has a mass number of 222. The atomic number of radon is 86. So the difference in that would be the number of neutrons. So when this breaks down, it loses an alpha particle. That means for the mass number from the parent nuclide has to go down by 4 because 2 protons and 2 neutrons are leaving. So we go from 222 to 218, and then the atomic number has to go down by 2 because 2 protons are leaving, so we go from 86 to 84. So during this radioactive decay, and all radioactive decay that include alpha particles, we can see the change here. The mass number goes down by 4 because the alpha particle has a mass number of 4, and the atomic number goes down by 2 because the alpha particle has a atomic number of 2. Okay, so you can see the 2 mass numbers on the right side. The right side of the equation gives us our products. Those 2 have to add up to what the parent nucleide mass number was. And then the 2 atomic numbers have to add up to what the parent nucleide was. Okay, so this is an example of how you would write a nuclear reaction that shows the process of alpha decay. The parent nucleide is the one that's the reactant. It's on the left side of the equation. and then the daughter nuclide, the one that's produced along with the alpha particle, they're both shown on the right side of the equation. Okay. During beta decay, what happens is that a neutron in the nucleus converts to a proton. So remember, neutrons are neutral and protons are positively charged. So basically what has to happen is a negative charge has to leave the neutron to convert it to a proton. So during beta decay, in the nucleus, a neutron converts to a proton and a electron is emitted from the nucleus. We're not really worried about the electron. We're only worried about really what's happening in the nucleus. So the mass number is not changing because of a neutron's converting to a proton, but the atomic number is changing. The atomic number is actually going up, right? Because we had a neutron and now it's a proton. So we have one more proton in the nucleus when this happens. Okay, so beta particles are typically written like this, which is interesting to have a -1 there, but that simply means that during this process, the atomic number is going to go up by 1 because the neutron's converting to a proton. So if we look at this process, phosphorus 32 is a radioactive isotope of phosphorus. During its decay, it emits a beta particle, and that beta particle is shown here. And remember, the mass numbers have to add up from the reactants to make the mass number, or excuse me, from the products to make the mass number of the reactant. So 32 plus 0 is still 32. And then the atomic numbers also have to add up. So 16 minus 1 is 15. So during a beta decay, the daughter nuclide has one more proton than the daughter nuclide has one more proton than the parent nuclide had. So the mass number actually goes up, and the atomic number goes up, and the mass number stays the same because protons plus neutrons are the same, because all we've done was convert a neutron to a proton. Okay, so in this process we can see that the parent nuclide, in this case, was phosphorus 32. It had an atomic number of 15. The daughter nuclide is sulfur 32, so it still has the same mass number, but now it's changed from a phosphorus atom to a sulfur atom because in the nucleus it's now got one more proton. All right, so that's the process of beta decay. So a lot of times radioactive elements will go through a series of radioactive decays until we get to a stable element. For example, uranium-238 is a reactive isotope, a radioactive isotope of uranium. There's a few of them. Radium-238 is one of the common ones. Radium-235 is actually the one that's used in nuclear reactors and things like that. But uranium-238 goes through, you can see all the different steps. So its first process is it goes through an alpha decay. You can see the alpha there. To make thorium-234. Thorium-234 is still a radioactive nucleus. It's not stable. So it goes through a beta decay to produce Pa-234. And then it goes through another beta decay to produce uranium-234. And then it keeps going, and you can see that each step, what type of decay mechanism it is and what the new daughter nuclide is. So this takes several steps and several radioactive decays to get to a point where you have a stable nucleus. Right? So hopefully that gives you some idea of radioactive processes. Radioactivity occurs when a nucleus is not stable, and that nucleus will break down at some point in time in an attempt to make a more stable nucleus. The new nucleus is called the daughter nucleus, or daughter nuclide, or daughter isotope, and it itself could be radioactive or it could be stable. Okay, if it's radioactive, it will go through its own decay process. All right, so I got a couple practice questions here, and they're simply writing nuclear reactions based on if it's an alpha process or a beta decay process. So take a minute and pause and try these. And if you're not getting them, or you get them and you want to come back and check, come back and check. So press pause and try them. Okay, hopefully you've tried these. So let's do this. So we now have uranium-235, and this is going to go through an alpha decay process. So I'm going to write my parent nuclide is uranium-235, and the atomic number of uranium is 92. I should have remembered that. We just did it. So I'm going to write uranium-92-235. I'm going to put my arrow. Okay, so that's my parent nuclide. So my daughter is going to be produced by the loss of a alpha particle. So we said the alpha particle has the symbol alpha with a mass number of 4 and a atomic number of 2. So the product, or the daughter nuclide, has to have lost 4 from its mass number. So it started at 235, so the new mass number is 231. And it has to lose 2 from the atomic number. So the atomic number was 92, and it's now 90. Okay, so when I add 31 plus 4, I have to get the reactant, the parent's mass number. If I add 2 to 90, I have to get the parent's atomic number. Okay, so if I look at what this element is, it's got an atomic number of 90. So I'm going to go to the periodic table and look up 90. And 90 is thorium. It's TH. So I'm going to write TH here. So the decay process for uranium-235 is going to produce an alpha particle and thorium-231. Thorium-231 is the daughter nuclide. And actually, thorium-231 is also radioactive, and it goes through an alpha decay process, but we're not going to do that. Okay, but this would be the equation that shows the chemical or the nuclear reaction of uranium-235 as it goes through an alpha decay process. All right. The next one is iodine-131 is used as a tracer in medicine. So we use it for imaging. Typically we use iodine-131 to test for thyroid efficiency. So this nuclide or radioactive isotope goes through a beta decay. So let's write its equation. 131 iodine, and iodine's mass number, atomic number is 53. Okay, so that's the parent nuclide. That's the one we're starting with. And it produces a beta particle. And remember, the beta particle symbol is beta. Looks like a bee with a tail. And it's got a mass number of 0 and an atomic number of -1. So iodine is going to break down into, the mass number is not going to change when we produce the daughter nuclide, but the atomic number is going to go up by 1. Right? So that when we do 54 minus 1, we get 53. Okay? So looking on the periodic table, the element that has an atomic number of 54 is xenon, Xe. So in this process, we produce a xenon atom, an isotope, one of the isotopes of xenon. That's going to be the daughter. I do not know if that's stable or not. but that xenon 131 is the daughter nucleotide. So that would be our equation for the nuclear reaction when iodine 131 radioactively decays through a beta process. Okay, so if you've got questions on this, feel free to contact me.